In previous class, we also discussed of MVT. In first, we talk about when MVT does not hold, when function is defined from R to R square, and then also we talk about when this one is hold. That means when functions are that means MVT are hold. We also talk about next. Now we also discuss when this MVT hold for a function Rn to Rm. Okay, we write it in theorem. So start this theorem. Let C be a non-empty subset. Let C be a non-empty subset of Rn. C be a non-empty subset of Rn, and let A B belongs to C, and let A B belongs to C, such that closed interval A B subset of interior of C. Let F C to Rm be a function such that f dash x exists for all x belongs to AB. Exist for all x belongs to AB. Okay. Then there exists C belongs to open AB such that inner product of FB difference FA here Y. There is some problem. How this problem create, I don't know. Who create this problem? Once someone bastard or create those problems, I think. But now this one is okay. So we're going to start about that. Inner product of AB difference FA Y equal to inner product of F dash C B difference A Y. Okay, for Y belongs to Rm. Now we also discuss this one. So how we handle this? We write this proof of this theorem. Let Y belongs to Rm and define fx equal to the inner product of fxy. Okay, and define a function fc to r by fx equal to inner product of fxy. Okay, for x belongs to C. Then if satisfies all these assumptions of MVT, then if satisfies all the assumptions of MVT when functions functions are from Rn to R defined. Okay, then what happened? Then there exists C belongs to closed interval AB such that FB difference FA equal to F dash C B minus A. Okay, then FB equal to here FB Y, here difference FA Y equal to F inner product of F dash C B minus A Y. Okay, F dash C equal to this one. Then what happened? Then this implies that this implies inner product of FB difference FA Y equal to inner product of F dash C B minus A Y for all Y belongs to Rm. Okay, so we erase that portion and going to further discussion about that. Since Y is arbitrary, so we have FB difference FA Y inner product of this equal to F dash C B minus A Y for Y belongs to R to the power m. Okay, so we also do this proof of MVT in higher dimension. Okay, so in this way we also discuss the how MVT in higher dimension create some functions which is also defined on Rn to R if we also create fx belongs to Rm and y belongs to Rm. So fx and Rm are y in our product, then this gives a functional value, and this one satisfies MVT, and we also getting our required result. Now we also discuss another way we write here and also going to prove of this another way, another important result. Okay, but here we construct some convex set. If U be an open convex set, we write here MVT and write this statement. If U be open convex set, okay, in Rn, and let f u to Rm be u to Rm such that f is differentiable on u, okay, then for AV belongs to U, there exists C belongs to this closed AV such that such that if if there exists a constant m, there exists a constant m greater than 0 such that norm of f dash x here L Rn Rm less than equal to m for all x belongs to u. Okay, then here something is mistake such that this one when when m greater than 0 be a constant. Okay, then what happened, then if here if ab belongs to and this one happen, then what, then norm of fx difference norm of fy less than equal to m norm of x difference y. Okay, so we also discuss here we erase that portion and going to how we handle this. Okay, fb difference fa mod of this less than equal to norm of f dash c here l r n to r. Okay, here norm of b minus a, then this one now fb difference fa less than equal to supremum of norm of f dash x, here x belongs to ab and l of r and r multiplied by norm of b difference a. Okay, then what happened, then we write here inner product of fb difference fa here y equal to inner product of f dash a theta b minus a here multiplied by b minus a y inner product for y belongs to Rm. This implies inner product of a plus h difference f a y equal to here f dash a plus theta h y for y belongs to Rm. Then this one equal to norm of fb difference fa less than equal to supremum of norm of f dash x belongs to open ab and multiplied by norm b minus a. Okay, here this one defined on Rn to Rm. So we also discuss this one now. If b minus if a less than equal to this one. Okay. Then this one is less than equal to a. So we write here. So what we write? Oh sorry, here Rn is better. Okay, because Rm is discussed in later. Okay. Then here the mod of this one is less than equal to R. Not this one is Rm because this one is inner product and these two are it belongs to Rm. Okay. So this one is supremum of mod of f dash x. X belongs to AB. Now we also going to observation something. Here we write for y belongs to Rm with norm y less than 1, and here if b difference if a y less than equal to f dash c b minus a y less than equal to norm of f dash c b minus a multiplied by norm of y by Cauchy-Schwarz inequality. By Cauchy-Schwarz inequality. Less than equal to norm of f dash c, norm of b minus a, norm of y. Okay. Then we write in above way, we erase that portion and we write here, since norm y is less than 1, so since norm y less than 1, then norm of every difference if a y less than equal to norm of f dash c, here L of Rn Rm multiplied by norm of b minus a. Now norm of a, L of Rn Rm equal to supremum of x not equal to 0. Here norm of ax divided by norm of x equal to supremum of norm of ax y divided by norm x, here x less than equal to 1. Okay, norm of x less than 1. So we now write this one. So we erase that problem. this one FB difference FA. Here y inner product of this less than equal to norm of f dash c l r n r m multiplied by norm of b minus a. Okay, this one is the required result. So we also write here from that this less than this one norm of a b difference f a less than equal to norm of f dash c l r n r m multiplied by norm of b minus a. Okay, then this one is the required result. Okay, this one is the required result for this one is the required result for, that means what we want, this one equal to norm of f b difference f a less than equal to m norm of b minus a, since norm of f dash c less than equal to m. Okay, so we get this result. So we also done this MVT higher order. That means first we discuss just Rn to Rm, then this one in a closed interval subset of interior C, and here we discuss one open convex set in Rn where f is defined from this convex set to Rn, then where MVT is MVT is MVT is valid or not, also checked here. Okay, if open convex set in Rn then also valid, otherwise in closed interval subset of interior of C then this MVT is valid. This MVT is represented in inner product. Here MVT is represented by this norm. Okay, so we also discussed today MVT portion. Now we also going to one important theorem, Banach Contraction principle theorem. Now we discuss here. Okay, where is this portion? I'm going to Banach Contraction principle. Banach Contraction principle. Okay, we know about this one is one important theorem, also discuss now. Okay, let xt be a complete matrix space. Xt be a complete matrix space, and let tx to x be a mapping such that dx d of tx dy difference of tx and ty less than equal to k difference of xy, or distance of tx and ty is less than equal to k d of distance of xy for all xy belongs to x and k belongs to 0 1 open, or 0 1 close to a construct, not a problem here. So then what we get, then t has a unique fixed point. T has a unique fixed point. Okay, how we prove it? This one is too easy. We'll handle this one now. Unique fixed point. Fixed point, how when one point is called fixed point, we know about that. F of x equal to x, t of x equal to x, then t has a unique fixed point. This fixed point is x. Okay, that means functional value is equal to this original value. Then we call about that this one t has a fixed point in this value, original value. Okay, now we're going to this proof of this fixed point theorem. So now start it. Let x0 belongs to x, then define a sequence. Define a sequence xn in capital X by xn plus 1 equal to txn. Okay, for all n belongs to capital N0, here n union 0, this is the domain, not domain, this one is the, that means n belongs to in this field. Okay, we have x0 construct and then x1 x2 x3 dot dot dot. Now what? Now d of xn plus 1 xn equal to d of txn minus 1 less than equal to kt of xn minus 1 less than equal to k square d of xn minus 1 xn minus 2 dot 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 less than equal to k to the power I d of xn minus I plus 1 xn minus I less than equal to dot 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 k to the power n d of x1 x0. Okay, n equal to 1 to infinity d of xn plus 1 xn less than equal to d of x1 x0. My summation n equal to 1 to infinity k to the power n, and this one less than equal to plus infinity. Okay, hence we erase this portion and going to discussion about that, and we also write xn is a Cauchy sequence. Okay, so what we get here summation n equal to 1 to infinity d of xn plus 1 xn, okay, less than plus infinity. Hence xn is a Cauchy sequence. Hence xn is a Cauchy sequence. Since x is complete, there exists x belongs to x such that xn converts to x. from 1 we get what we get. Obviously get that here x equal to dx. Okay, because in 1 also write xn plus 1 equal to txn, and here xn equal to a converts to x, so xn plus 1 converts to x, and obviously tx, that means txn converts to tx, so then we going to be right here from what we get x equal to tx. Okay, now we construct uniqueness, unique fixed point. That means t has a unique fixed point. We also prove this one, unique fixed point, uniqueness of this fixed point we prove now. Let y belongs to x such that ty equal to y. Okay, then how we write this one? Then d of xy, distance of xy equal to distance of tx ty. Okay, then this one less than equal to k of distance of xy. Thus here txy less than equal to k multiplied by, here k belongs to closed 0 1. Okay, then what happened? Then we write talk about that these 2 points are equal. Okay, therefore what we get? Therefore t has a unique fixed point. T has a unique fixed point. Okay, we now stop here. T has a unique fixed point. Now we also going to be discussion about another portion, but this one not today. After certain time we also discuss this one. Now we also stop here.